Okay. All right. So, next one, optics. Optics, and I'm going to tell you straight up, and I've had this discussion with some of you, is that I work about optics. It's kind of like a love-hate relationship, more so than about any other unit that you have. In the sense that either you really like it and you understand it and you think it's cool, or it's like the bane of your existence. Okay?
So it's that one.
There's not a lot in between. Okay? Some people are indifferent to it, but it tends to be fairly polarizing. Like, man, this is cool, or wow, I'd rather have my teeth pulled without painkillers than be radiated. I'm just telling you, okay? Now, where you fall on that spectrum, that's up to you. So, let's start with what optics is. So, there's two main optics sections. You have mirrors, and you have lenses. Okay?
Like glasses?
Yes. Okay? So those are the two broad things that we're going to deal with. Mirrors and lenses. Both of them involve somehow transforming the path of light. So one of the big debates that existed in science was, how do you treat light? Is it a wave? Is it a particle? Okay? And you can kind of make the justification for both. So what we're going to do on optics is we're going to treat light as like a ray. In other words, ray of light traveling in a straight line. Okay? Now, if it hits a mirror, it could bounce off of that mirror. Okay? Which is what allows you to see images in a mirror. So when you're getting ready in the morning and you're standing in front of a mirror, okay, so you're here, okay, and you're getting ready. So what's happening, that it gets a little bit complicated, what allows you to see you in the mirror is that light's going to come in, it's going to bounce off of you. It's going to bounce off of you, it's going to hit the mirror, and then it's going to bounce back, okay? This is important. For you to see anything in a mirror, it has to bounce back. Now, initially, what we're going to deal with is called plane mirror, or flat mirror. Okay? So, on a flat mirror, here's your mirror, and you can kind of visualize this as being like a ball. So, when that ball comes in, you typically draw what's known as a line that's at a right angle, okay? The normal line, which is a right angle to the mirror. So imagine this, like I take this ball and I throw it at an angle and it's going to hit the mirror here. And then what's it going to do? It's going to bounce off like this, okay? So what we're going to assume is that this is your incoming line like this, and this is what's known as theta I. And the I stands for incidence. Okay? And then you have off of that theta R, and that's the angle of reflection. Okay? Now, if you are on a flat mirror, these two angles are symmetrical. Okay? That makes the math easy. So the angle of incidence is going to equal the angle of reflection. So the bigger the angle is, obviously, as that's incoming, the bigger that's going to be. So this is where mirrors get weird. Okay? So then try and spin that camera, kind of shine it towards that glass window. Okay? So I can stand here and I can see myself in that glass. Okay? So what that means is that some of that light that bounces off of me, a lot of it's going through, so if you were on the other side, you can see me. But I can also see myself. So that means some of that light is bouncing off of this. Okay, now, Popcorn, I need you to stand up kind of right here. Okay? Now, Popcorn, can you see me in that mirror? Okay? Now can you? Now, Popcorn, move over a little bit. So, there you go. Okay. Now can you see me in the mirror? Okay. And I can see you, right? So here's what's happening. Is that light is bouncing off Popcorn. It's hitting that. It's bouncing off. I can see her and I can see me. Okay. Now, so at this point, imagine that you have a triangle. So that light is going in, hitting that, bouncing off. We have this triangle. Now, Popcorn, I'm going to move over a little bit. Okay? I'm going to move over here. Now, can you see me? Okay? Now, I can see her. Now, I can't see myself in the mirror. But I can still see Popcorn. Okay? So, what I've done is I've broadened out the base of this triangle. Okay? Now, I'm going to keep going. Can you still see me? Okay. Now, can you still see me? Okay. Now, can you see me?
No.
Okay. Now, oddly enough, I can't see Popcorn either. Okay. But if I do this, can you see me?
Yeah.
Now you can't. Angles. Okay. It's all about the angles. So, here's the story. So, as that light goes in and bounces off, if I'm going, and you keep this in mind, especially if you're driving behind a large semi-truck, okay, and you're trying to pass them, if the rule is, like, Popcorn, you can see me, right? And I can see you. Can you see me? But I can't see you either. So if you're behind a truck and you can't see their mirror, guess what?
They can't see.
They can't see you either. Okay? Right? So that's the rule. So if you can't see the mirror of a truck when you're passing it, they can't see you. But if you move where you can, then they can see you. Now, Popcorn, I want you to walk forward a little bit, about halfway. Keep going, keep going. Okay, stop right there. Okay, now, can you still see me?
Yeah.
Okay. What now?
I can't see you.
Okay. Now, if I move directly behind you, you can see me, right?
Yeah.
Okay. But if I move over too far, what happens?
I can't see you.
Can't see you. Now, walk a little bit closer. Okay? Now, kind of stand right there in the middle. Now, I'm going to move, like, over here. So now, can you see me?
Yeah.
Now, you can't.
I still can.
Can you see me?
Yeah.
Can you see me?
No.
No. Okay. So, what we're doing is now, before when she was here, it was symmetrical. So, the angle coming in was symmetrical because she was the same distance away. But as she moves forward, but it's still the same geometric relationship. No matter where she is, if she can't see me, I can't see her. Now, Popcorn, take a little step forward and then move to your right, a couple of steps. Okay, whoa, right there. Can you see me?
Yeah.
Okay, now move to your left. Stop. Can you see me?
No.
No. So, depending upon where she is, even though I'm not moving, that determines whether she can see me. Now, move to your right. Whoop, you can see me now, right?
Yeah.
Now, you keep going. Another step. Still see me?
Yeah.
Another step. Another step. Can you still see me? Okay? Because I can still see her. So, now we're changing the geometry of this. So what has to happen is that these angles, you have to be within that dome. Now, Popcorn, from your perspective, can you see Olivia?
No.
Why not?
Does it?
The angle's wrong. Now, Olivia, can you look in there and see Popcorn?
No.
Can't. Doesn't work. Now, move over a little bit. Don't leave me out of this. Let me know when you can first see Olivia.
I got it.
I can see him.
Okay? You can see her, right? So now, look at that difference in the gas. But the idea is still going to be the same. Well done. Thank you, Joe. Okay.
Sorry, didn't move it.
Now, actually, keep going that way. Keep going that way. Now, this is where it gets weird. Okay? So, imagine that that's actually like a big full-length mirror. This is what will mess with you, and maybe cause you to like end up in the corner sucking your thumb. Now, I raise my right hand.
Oh, God.
Oh Lord! Oh Lord! Then it's
Okay?
left.
Now, visualize this. Okay? If that was an actual mirror. So if I am, let's say, 5 meters away, I'm 5 meters away from the mirror. If it's a flat mirror.
Okay.
I'm going to appear like I'm 5 meters on the other side. Okay? This is 10 meters, right? So if but now, visualize this. You got to stay with the vision. Imagine that that's not a mirror. Imagine that there's a duplicate of me on the other side of a piece of glass. Okay? Right? Duplicate of me is just a plain glass. There's no mirror. And we want to act like it's a mirror, though. So if I'm the person on the other side, okay? So visualize this. I'm going to raise my right hand. What would the person on the other side do?
Left hand. Left hand.
They would have to raise their
left
hand.
Yo.
Okay? So if we were doing that without the mirror, I would raise my right hand, right? But the person on the other side would raise their left hand. Okay?
It's like a mirror.
Now, so when I look at this,
Everything is backwards.
if that was an actual mirror, I cannot tell the difference whether I'm looking at an image or there's a duplicate of me on the other side.
Yo.
So the mirror, moral of the story is under the mirror. So when you're getting ready in the morning, it's like, man, am I seeing a reflection? Is there another me on the other side of the glass? Okay? Just saying. Because you can't tell the difference.
So this is not going to be on the test.
Imagine you're just out of you're allowed to say.
It's okay, I don't like
Okay.
We
have to get in the mirror.
All right. Give that a spin. So here's what you need to remember as when you're dealing with flat mirrors, is that the angle of incidence is always going to equal the angle of reflection, and the angles are always measured from a normal line, okay? 90 degrees to that. These two angles are symmetrical. And so if you go back to what happened with popcorn tonight, if you have a mirror and like you're here, and if you can draw a symmetrical line and you can see that person on that where that bounces off, and you can see that person, they can see you. But if I'm like over here, and then if I try and bounce that line off of here and have that come off like that, I'm too far out. I couldn't see that person. Is the light still going to bounce off of it? Mm-hmm. Yes. But I couldn't see that person because they were outside that symmetry line. Okay. That's the first part of it. All right. Now, more work with the index of refraction. Now, I'll show you this equation, and then we'll explain what it means.
This one, right? That's a small one.
Nice.
Yes. Yeah.
Oh,
Are you out? I'll have these videos posted.
I don't know, probably home.
you got scared.
Dude, I'm tired of going to bed.
I know.
Okay. So, when you get into this concept known as index of refraction, and this is why we briefly hit on this, now we're going to spend a lot more time talking on it. So, this is air, and then I'm going to draw this a little bit bigger, and that's going to hit some glass. Okay? And what we want to figure out is what's going to happen once it hits the glass. So let's start with this idea. The index of refraction of glass might be, I don't know, 1.8, something like that. Okay? There's a chart in chapter 18. Or chapter 17.
That's the
this index of refraction. Okay? I can't remember if it's 17 or 18. But the indexes of refraction. So here's the point. Glass has an index of refraction bigger than 1. So what does light do? Slows down. Okay, accelerates. Okay?
Wait, what?
Do we change the frequency or do we change the wavelength?
Wavelength.
Wavelength get shorter, wavelength get longer.
Shorter.
Wait, let me think.
Okay. So the speed of light
Wait, velocity equals wavelength.
is wavelength times frequency, right?
So wavelength is that.
So the new velocity is going to be less than the speed of light, but you're going to have the same frequency. So to create a smaller velocity with the same frequency, the wavelength has to get shorter. Okay? So in a new medium, the wavelength gets shorter. How do you know the frequency stays the same?
Color doesn't change.
Yeah, if you were to stand on the other side of that glass and look at me, my shirt would still be blue. Okay? Right? It's not going to change. It looks like, oh, those are glass. Why can't shirt look orange? Okay? It's going to be the same. So, what's going to happen is that because it's going to slow down, the light is going to bend. Now, to show that, stop you on the camera. We're going to go down